All right, so a cut edge is an edge in a graph whose removal disconnects a component of the graph. And this is one of the reasons I wanted to talk again about connectedness, the idea of being a connected graph. In other words, if we remove one of the edges, I change my graph from being connected to being disconnected. Okay, so an edge that has that feature is called a cut edge. And I'll draw you a picture here in just a second after you guys have written this down. All right, so we have seen graphs that have cut edges, and we have seen graphs that do not have cut edges. So I'm going to draw you a graph that actually has a cut edge so we can talk about what that would look like. So let's say that you had a graph that looks something like this. So this is not perfect, but imagine it is. The delay time on the wireless in this room is bizarre. I don't understand it. I've got dots all over my screen. I mean, oh, there they are. See, there you go. Okay. All right, so if we were to cut or remove an edge, so let's say that we removed this edge right here. Okay, so if I cut that in half, or I just took that piece out, or whatever, then I would end up with a piece along the top. It's two vertices. And there's no way to get from either one of those vertices to the pieces on bottom, right? Because I took the only edge that actually connected them together. So this is an example of a cut edge. Yes, Mark?
How are they connected, though, without a vertice between the top two?
Oh, I need one there. Hold tight. How about that?
The degree of among the cut edge that determines it, not really the vertice. I guess the vertice.
You need the vertice in order for it to actually be attached, which Mark was right. Yeah, I should have drawn it. So this one actually has one more cut edge than just that one, though. So, I mean, that one works just fine. That certainly cuts the graph into two pieces. But there's actually another one. So let me put some letters on my vertices so we can talk about them. Let's say that this is A and B and C, D, E, F, and G. So we've already established that BE is a cut edge. What's another cut edge in this graph? EF is, yes. And it's the only other one. Any of the other pieces, if I cut those particular pieces, for instance, let's say I cut this one right here. I don't have, well, there's nothing that connects D to it. That's true. So that one actually would have a problem as well. So, yeah, that one actually would have a problem as well because we still would have D that would be unconnected. Let me give you an example of something that doesn't have any cut edges, though, too. Make it real simple.
So you're only allowed to cut one. There's only allowed to be one cut edge.
Well, no, you can have multiple cut edges, but you want to think about cutting them one at a time, which I think is your question.
Right, yeah.
Yeah, so if you were to cut, you only cut one at a time, and if you can cut one of them and it disconnects the graph, then it's a cut edge.
Yeah.
Yeah. On this one, we don't have that feature. So Damon told me I can't actually cut DE on the last one, and he's right because it disconnects the point D from the rest of it. But on this one, if I cut, for instance, this edge right here, A and D, still okay. I can still get from A to D, right? I just can't get there in one fell swoop. I have to go all the way around. All right, this is the thing that happens when you have detours in a city. You can still get where you need to go, but it's going to take you twice as long to get there, right? Okay, so we've got that issue going on here. All right, so let's do an example that I've actually got in here. Here you go with a example. We're going to identify all of the cut edges in the graph, and if there are none, we say so. There actually are some. So tell me, what is a cut edge in this graph? EF for sure. What else? FG would be, because it would disconnect point G, kind of like we did on that last one. And FC. Any other cut edges? Everything else is good, right? The other piece is this kind of the rectangular or square piece that I kind of referenced in my last example. Anytime I cut one of those edges, I just still have a circular path that I can get there longer. Okay, so I have 3 cut edges in my path, in my graph. Fleury's algorithm depends on cut edges. That's actually why we brought it up. So this one's got a lot of writing, so let me read what's going on while you write. Yes, Glenn?
You had FG listed as a cut edge, so you can cut a vertice out of the entire graph, not just a section of the graph?
If I cut FG, I would be removing the edge, but the point G still remains.
Okay.
So in other words, G could still be part of the graph. It just doesn't have any edges attached to it. It'd have degree 0. It's not very interesting, right? It's the island in the middle of the ocean. We can't get there by driving along a road,
But it
kind of an issue.
still is
But it's still there.
a
It's Hawaii.
cut edge. Okay.
We can't drive to Hawaii. I guess you could drive on a boat. That might be kind of tricky. But yeah, you can't actually drive there. So you couldn't actually get there by a path. But
Bless you.
yes, it's still part of the graph. What's that?
Bless you.
Thank you.
What are you talking about?
Slow route or the quick one?
Okay. Let's look at Fleury. I think that's how you pronounce it. That's what I'm going to say. This is Fleury's algorithm, okay? So you start at any vertex, and you go along any edge to any other vertex. So that sounds pretty arbitrary. You got lots of choices, right? And when you move along that edge, you sort of erase or cut or remove or whatever the edge. In other words, you're not allowed to go back along the edge, okay? And then in the revised graph, the graph without that edge now, you choose another path, another edge that you go along. Unless there is no other option, you do not choose a cut edge, okay? The process for this is lots easier than it even sounds, but this is what happens when you put steps to something sometimes. And so anytime you pass along a path, anytime you pass along an edge, you remove the edge, okay? So in other words, you can't get back. So the image I have in my mind as I'm describing this is every now and then you'll see something in some action movie where they're on a bridge or something. And every time they take another step on the bridge, the plank that they were on just on, it falls. I don't know how they're going to get back across the bridge. Probably ride the dragon out of the castle. Sorry, I'm thinking Shrek. So you've got this image, right, of whatever you're purposely standing on right now, it's going to disappear once you take a step off of it. Are you following with me? Okay. So jot down these steps, and then we're going to do one, and you'll see that the process for doing this is actually not as complicated as the process sounds.
But it does fly out.
All right, so if there's an Euler circuit, do you remember what an Euler circuit was? I told you that this creates a circuit. But what's an Euler circuit? It doesn't actually touch all the points. I mean, it will, but it actually uses all the edges. That's the issue. It uses all the edges. So we have to use all the edges, and we have to use all the edges only once. Otherwise, it wouldn't be a circuit anyway, right? And then we have to return back to the starting spot. So if there is an Euler circuit, this process will find it. Doing this process will find the circuit. Okay? You ready to give it a try? As we work the process, though, the graph gets really messy, especially if the graph is messy to start with, which it is on this one. Agreed? Depending on when you printed this out, K may be missing in the middle of that box, so just add it in if it is, because that was an omission when I first had it posted out online. All right, so the first issue is it tells you that you're going to start at A. So we have to start at A. I know that sounds like a dumb thing to say, but we make sure we start where it says so, okay? If it didn't tell you where to start, you can pick whichever you'd like. So we are actually going to start our graph at A. So we're going to start here. And we're going to go from here, and we get to pick whichever edge we want to go on, which means everybody's answers could be different. So let's make them all the same just for the sake of clarity in class today, and somebody pick me an edge.
H. A to H.
A to H. Okay, so we're going to go, whoops, let me write it down here. We're going to go from A to H. Okay, so when I go from A to H, it's a little bit bolder than I should use. Let's try that. We're going to cut edge AH. And your book likes to use squiggles. If you have a different color to use as squiggles in, it's going to make it lots cleaner. So again, you've got some colors you can use. So from H now, I only have one other option. I have to use the option that I have. There's only one other edge coming out of H. So I'm going to go from H to where?
G.
To G. So I'm going to cut this edge now, right? I'm going to remove that piece. Now G has 3 options.
Got it.
We can go from G to
G to A.
G to A. What else we do? G to J or G to F. Now, we actually have to stop and ask ourselves, are any of those actually cut edges? In other words, do they disconnect this graph? No, they don't. You're right. So, yeah, if I cut any of those edges, I don't have any disconnected graph yet. So I can actually go on any of those edges. So somebody pick me one.
G to A.
G to A. All right. So we've eliminated this sort of triangle in my shape now, right? And we're back at A, and now we have 2 options. We can go from A to F or A to B. Again, neither one's a cut edge, right? Tyler wants to go from A to F. Now what, Tyler?
F to J.
You want to do F to J? Tyler's going to pick our Euler circuit for us today. Okay, that looks good.
J to G.
J to G. I only have one option. Now, I actually have 2 options after G. Oh, no, I don't anymore. I'm sorry. I take that back. I've got to go G to F, don't I?
Yes.
I'm running out of choices so quickly. And I only have one choice after that, don't I? F to where?
B.
F to B. Now I have 1, 2, 3, 4 choices after there, so somebody pick me one. E?
E.
How about after E?
D.
Yeah, that one I have to, right? No choice there. D has a choice, though.
K.
You want to do K?
Yeah.
C would be fine, too. We could do C. K only has one choice after it. After K, it's
B.
B. Okay. All right, someone else take a turn. Tyler's going to stop taking a turn.
B to D.
Glenn, okay, B to D. I already have, oh, this one right here, you mean. Sorry. Yes. So B to D. And then D to C, I don't have a choice on that, yeah. B to D to C. Did I already write that down? I don't remember doing it. Okay. After C, B, back to B, and then I'm back to A, and I'm done. And so by process of elimination, sometimes I have choices, sometimes I don't. There are a few cases where if we had done something different, we would have encountered the whole cut edge problem, and we couldn't have gone down that path. We didn't encounter any because of the values you guys chose. But this would be one Euler circuit, because I didn't use any of my edges more than once, because once I yellowed them out, I didn't go back, right? And then I've created a circuit of doing so. Yes, Kristen?
On one of your things it says F to H.
Oh, did I write something wrong? I may have. F to J, and then to G.
Okay. That
Let's
makes
fix
sense.
it. Sorry about that.
That's okay.
Okay, is anything else that I messed up on? It could be. I've gotten about 4 to 5 hours of sleep the last 5 nights, so you just tell me if I make another mistake. All right. This is a note about Euler paths. This isn't worded exactly in your book, so make sure you jot this down. If all of your vertices do not have even degree. Okay, so if they do have an even degree, we already know then that there's an Euler path. Okay, that was something else we talked about earlier. So if they all have an even degree, that's fine. But if they don't all have an even degree, but there are just two that have odd degree, we can still create an Euler path, okay? We won't be able to get an Euler circuit. That will not be possible. However, you can still get an Euler path, but you'll start at one of the odd vertices, and you'll end at the other one. And I think I have an example of one of those. Yeah. Let's take a look at one. So first you have to figure out if you're in this case, which means you have to look at a graph and actually figure out what each vertex degree is. So let's start with A. What is the what is the degree of vertex A? How about E?
6.
6. F?
2.
2. G?
2.
D?
2.
C?
3.
And B?
3.
Okay, and I think BC got left off on some of the copies, so if you printed this early before I sent that last email that said print it again, just draw BC in there and we'll all be good, okay? All right, so they're not all even degree, correct? And we had I don't know if it was a theorem technically, but we had a statement earlier in this section that said if they're all even degree, a circuit exists. If they're not all even degree, a circuit doesn't exist. So there is not an Euler circuit, okay, agreed? But because I only have 2 of odd degree and everything else is even, I will have an Euler path. So I will be able to do what I did in the last problem. I just won't be able to start and end at the same place. I'll have to start at one of the ones with odd degree and I'll have to end at the other one. So pick me an odd degree point that you would like to start at. B. Tori says B. So we're going to start at B this time. And again, we have to go along the edges that don't disconnect my graph. So I can go from B to what? B to A or E or C. So somebody pick one.
Well, since we have to end,
E.
It won't affect anything. We could still go to C, even though we have to end there. What do you want to do, Tyler?
E.
E? Okay. We're going to cut right through the middle of the graph. So we're going to do B to E. Okay. Where do you want to go after E? Someone else. C? All right. So we're going to go over here to C. So here's to C. After C, where are we headed? A. And after A? Okay, so let me pause here to make a comment. I do not have a choice right now. If I go from A to B, then I'm forced to go back to C, and I didn't cross everything, did I? So here is a good example of a place where I don't have I don't have freedom, right? I actually have to go one way, and it isn't because there's not another way that exists. It's because another way won't get me everywhere I want to go. Okay, so I have to go from A to E, right?
Could also go to A to D.
That's true. I could go from A to D, but I just cannot go to B. I should say that. Yeah, so let's do AE, because that was the one where somebody said that one already. What's after E? What's going to happen after E? Well, I don't have to go to F, but I have to go to F or G, right? For the exact same reason as what we discussed before. I'd be stuck, and I would have actually crossed something that would cut the graph, and I'd have no way to get back. So E to where? F? All right, so E to F. Now I don't have a choice because there's only one path next to go along. F to G. After G, back to E. After E, that will take me to D. And then D will go to A. A will go to B, and then B will go to C. So I created an Euler path. It's not a circuit because it didn't start in the same place, but I didn't cross any edges twice, and I did cross all the edges. Okay?